Today we will be discussing Physics 251, Week 4, Video Explainer, problem number 85. In this problem, we are tasked with finding the most efficient way for a rescue crew to save a drowning child who has fallen into a river. Based on some of the givens in this problem, which I've highlighted in red here, we can tell that this problem is going to be relating to a kind of reference frame and relative motion problems. So these problems were covered in our week 4 lecture from pages 29 to 38 here. So if you have any questions throughout my explanation, feel free to go back to that lecture and take a look. All right, well, let's go ahead and get into the problem. So here we have a little diagram that I've drawn out to kind of help depict what is going on in this situation. So at first it was a little bit hard for me to grasp exactly how this problem was laid out. But after a little bit of thinking and quite a little bit of drawing, I was able to kind of sum up what I think is going on here. So here we have in red, this is going to be our rescue crew. So we have the dock right here at this point, right here. And this is going to be 1,500 meters upstream from the child who is 200 meters away from the shore. So this child is going downstream at 2 meters per second. We're tasked with finding the angle right here, theta, at which the boat will be able to intercept the child and prevent any further damage. So let's get into it. So we have our givens right here. I've written, this is D stands for our distance in the y direction and the x direction. So it's going to be helpful for us to think of this whole thing in the coordinate plane and kind of go from there solving trigonometrically. So this problem, that being said, this problem does involve a lot of trig. So we're just going to have to remember SOHCAHTOA, and since we're talking about degrees here, we are going to be using degrees in this problem. So, all right, so we're going to be solving for theta here. And this is just this initial angle without accounting any velocity or any relative motion in to play. So we're just solving for this baseline angle out of this triangle. So we're just going to take the inverse tangent of 200 divided by 1,500 and get 7.59 degrees. So from here, we can begin solving the x and y velocity components of this problem. So we're going to start here. We're going to solve for the angle or the velocity of the boat relative to this angle right here. So we're going to get the x component of the velocity. So we're going to take -8, and it's important to remember that this is -8 here, because if we look at this and we're thinking about this in our coordinate system here, with this being 0, then this velocity is, or this vector is going in the negative direction, negative x direction. So it's important for us to note that this is a -8 right here. So anyways, we're going to solve that out. We're going to get -7.93 meters per second. From here, we're actually going to add the velocity component for the river in order to make this balance out to -5.93 meters per second. From here, we can go ahead and get the y component of the boat's velocity, which is a lot simpler. Just taking the sign here, and we're going to get 1.06 meters per second. From here, we're going to solve red theta, the same theta that's up here, in the context of the velocity, and we're going to take the inverse tangent of both of these velocity vectors, the x and y components, and the absolute value of the x and y components to get 10.13 degrees. All right, so the angle at which the boat needs to leave the dock is 10.13 degrees. Thank you for watching, and I hope you found this video helpful.